going to go over setting up the Euler formula, because typically this is where the students sometimes have issues with the method. So I'm not going to maybe compute all the points. Maybe I'm going to compute the set up the first point or so, but I'm going to focus on how you write this down in terms of what you have in the actual problem. So let's put two examples here side by side. So suppose dy dt equals let's say y squared times t, and then y of 0 equals 1. Let's do another one, and the step size, let's say it's 0.1 here. In another example, let's say dy dt equals cosine of y, and let's see, y of 0 equals 1, and then the step size, let's say, is equal to 0.5. And sometimes in the exam problems I may put the step size value much bigger just to make the computation easy, because my style is to actually make the use of the calculator almost not necessary in the exam. So although in practice, of course, a big step size h again will create lots of big errors in the computation, I may choose a big h just to make the computation easy, because the goal in the test, of course, is to show how you apply the formula correctly. And let's say dy dt equals sine of t squared plus y, and then let's say y of 0 equals 3, and like I said, let's say the step size is 2, again, which is going to be an insane size actually. That'll give you a huge error of computation, but just to emphasize where each path comes into play when you write the Euler formula. So once again, what is the right hand side? What's f of ty in problem 1? So f of ty is y squared t. So therefore, in the Euler formula, f of t n yn will be yn squared tn. It's very important to take your time to write down the Euler formula according to what you have in the actual problem, right? Especially the y's. I mean, the one with t here, I mean, that you can just do it in your mind when you fill in the table, because the time steps, I mean, the time values are just separated by h, right? So that means, let's see, yn plus 1 equals yn plus h, which is 0.1 in your case, and then f of t n yn, which is yn squared tn. So I hope that makes sense, and you can write in the table right away, put the time values, right? So the initial time point is 0, step size is 0.1, so keep on adding 0.1 to the time values until you're happy with generating as many points as you want. So in the homework, don't generate more than 3 points. I know that the homework states, use small h and generate tens of hundreds of points. Don't do that, because it becomes too repetitive. So in the homework for this lesson, generate 3 points per problem, and also pick your own h. You don't have to use the h given in the problem, because I think in some problems they suggest taking h 0.01 or something like that. Just a single h value, not multiple ones, as they say in the problem, and just 3 points to generate here. So what about the y values, right? So the first value of y is 1, and then you can start using this main formula, right, to update the values of y. So for example, y1 will be the previous y, which is 1, plus 0.1 yn squared, which is 1 squared, times t naught, which is 0. So this is easy to compute by hand, because this is times 0, so y1 will be 1. Now the next one, y2, comes from the previous y, which is 1 again, plus 0.1, previous y squared, which is 1 squared, times previous t, which is 0.1. So this is actually 0.001 plus 1 is 1.001. So you get the idea, right? I mean, you can keep on going, generating the other points. I didn't compute this one before, but let's just write it here. Previous y, 1.001 plus 0.1, which is h. Y squared, 1.001 squared times t, which is 0.2. And then you can use the calculator to compute this and put it here. Now notice sometimes it happens that there is no t on the right hand side. That's perfectly fine. When you write down f of t and yn, so f of ty is cosine of y, f of t and yn is simply cosine of yn. So it doesn't have to depend on t necessarily. I mean, the Euler formula works just as fine. So it looks like this: yn plus 1 equals yn plus h, which is 0.5 times f of t and yn, which is cosine of yn. So basically, in your case here, although you should write the time values in the table, the y values don't depend on t, because the derivative doesn't depend on t. So when you write your table of values here, fill in the first row as before with the values of t separated by h, and then the y values will be updated from this formula, right? So for example, the next one, y1 would be y0, which is 1 plus 0.5 cosine of yn, which is cosine of 1. And I don't know what that is. I mean, you have to use the calculator here using radians, right? Because the angle is measured in radians. Let's set up this one as well. So f of ty is sine of t squared plus y. So of course f of t and yn is sine of tn squared plus yn. Let's put the time values. This time, as I said, h is kind of big, so it starts from 0 and you keep on adding h, which is 2. So the time values are 2, 4, 6, 8, and so on. First value of y is 3, and the Euler formula would be yn plus 1 equals yn plus h, which is 2 in your case, sine of tn squared plus yn. So let's write at least the first value. So y1 equals y0, which is 3 plus 2 times sine of t naught squared, so that's 0 squared plus yn, which is 3. Once again, I don't have the calculator right now, but sine of 3 again can be computed with decimals, and you can fill in the rest of the table this way. So that's all for today. This is the approximated method of solving differential equations. So for now, you know an exact method, which is the separation of variables, and then an approximation method, which is the Euler method. We're going to start chapter 2 pretty soon. So we're going to deal with what constitutes a linear equation, because the majority of the course, pretty much the rest of the material, will be focused on solving linear equations and linear systems of differential equations. That's one of the most important part of the theory of differential equations, to know how to deal with linear equations. They are important on their own, but also the nice thing about them is that there is actually a complete theory of how to solve these linear equations, which we don't have in the case of nonlinear ODEs. So that's it for today. I'll see you soon.